Okay, welcome to Origin Seminar. So today's speaker is Dr. Taran Esplin. He's got a PhD 2017 from Penn State. He worked with Kevin Luhman. And then he was an inaugural Street Matter Fellow at Stewart Observatory. And that's when we met Taran. And now he's working with Chad Bender about NUID, but a very high resolution spectral. Okay, so he's interested in a lot of things in star formation, nearby star forming regions. I was asking a question about Taurus, but he's working on a lot of stars nearby from like brown dwarfs. And now you're even working on brown dwarf atmosphere, am I correct? And interested in like Gaia initial mass function, disks, and orders of near stellar population. One interesting thing I would like to comment is that Kevin was a graduate student here. So I think you are technically academic tree-wise George Rickey's academic grandson, am I right?
That is correct.
Yes. Okay, so we welcome Taran, and we'll hear about the Corona Australis complex today. The floor is yours, Taran.
All right, thank you. I want to talk about this region. It's a region that I've been working on since 2016. So I actually started it as a grad student, and I finally submitted the paper last week with all of this data. And so this is my celebratory talk on the subject. So we will start with just introducing the region because it's not a very famous one. Here it is. There you go. Now you've met it. It's made out of a cluster centered on the Corona Australis dark cloud. There's only 3 B stars, so it's actually a very small star-forming region. But it's actually one of the closest, but because it's small and it is generally ignored in most studies. So here we have like an image of the galaxy in extinction, and you can highlight the nearby star forming regions. And so first you notice that they're actually quite large on the sky. And then you'll next notice that Corona Australis isn't even labeled on this. So I'll label it for you. There it is. You can see that it actually is a distinct feature on this on the sky. It's just dwarfed in comparison. So in 2019, the region consisted of the Cornet Cluster and a few off-cloud members. So this is from a recent paper that was an ALMA study of the region, and I just included this to give you an idea of the density and the distribution. So that's that same cloud that we saw, and that's the coronet, which is the clusters around the B stars in the center of the region. And then you can see around the edge, there's just a couple of other stars that have been identified that are young and appear to be part of the region. Back then, and for quite a number of years, actually, there's been evidence mounting that the region doesn't have a consistent age estimate. So this is from that ALMA paper from 2 years ago, and it's showing the dust mass cumulative distributions. So it's basically showing the percentage of stars in the region with a circumstellar disk, how many have more mass than the limit, right? So here it's saying almost all the stars have at least this size of dust. So this has a bunch of other regions on it, and I've labeled their approximate ages down the side. And this is a known fact that the dust mass of a region will, in general, decrease over time. And so you can see that you have these cluster of these young regions, and then you have upper SCO sitting down here at 10 megayear. And then Corona Australis, which has been aged at around 2 megayear, is sitting down here next to upper SCO. So this paper talked about it and tried to come up with ways of how to get the disks to be smaller without making the age any older, because there's a lot of evidence that says that the stars are actually quite young. And this discrepancy has been seen for quite some time. Here's just a list of a couple of other sources that noted that the circumstellar disks just don't appear to be the right age. And then enter Gaia data release 2, and everything got extremely more complicated. So this is an image from Gaia et al. 2020, and they published something that I had noticed independently, and they beat me by quite a bit of time. That's the way it goes. And they noticed that there's actually a lot of young stars in the region. So this blue cluster here is the Coronet before, and they discovered that there's actually quite a number of young stars in the region just to the north of the cloud. So they threw some statistics at it. They took the proper motions and the parallax and tried to identify the candidates that way using a Gaussian mixture model, and published the claim that there are these two populations were actually, so these colors are going to be the same here. So this is the blue, this is the red, that there's actually two kinematic populations, and that and so they're an independent cluster, or at least a related but independent cluster. And so their statistics machine said, yes, we favor, there's two populations. I mean, you can see it by eye. And then said, well, let's look at other things. So they took their photometry and did some SED fitting to theoretical spectra, plotted them on an HR diagram, and said, well, they appear to have about the same age, although the medians of the two populations are 5 megayears and 6 megayears, with the off cloud being slightly older. I, of course, have extreme reservations about the method of age dating. I know it's a very common one, but I dislike it intensely. I mean, to point out, you know, they get 5 or 6 is the median, and you see that all the older stars here are lying around the actual 10 megayear line. That's a sign that the models are wrong, not that your method is wrong. But anyway, we'll mention that again. We'll come back to this age problem of the regions in a little bit. So we're going to now talk about my study of the region. And I'm going to present it as if I was just responding to the Gaia et al. And then doing a bunch of other stuff about the region. And that's not what happened in true history, but it will be a better story and a more cohesive story about what we can learn about this region. So we're going to start with just looking at the Gaia data in the early data release 3. And we're going to test, we'll start off by testing whether those Gaia et al. Populations are real. So to start off with, a thing that is forgotten a lot of times is that proper motion is not actually linearly related to 3D space velocities. So the stars are moving, they're doing their thing in real 3D space. But when we measure proper motions, we're measuring proper motions on a celestial sphere. So those 2D spherical motions do not relate linearly to 3D space motions. And if you have stars that have the same space velocity, but are just on different portions of the celestial sphere, their proper motion will be completely different. So what we have here is the Gaia et al. Populations. The colors flipped from what we showed previously, but I hope we can all follow that along. And these are their two populations identified. So you can see this is proper motion in right ascension versus parallax. And then here's the proper motion in declination. And then we have the actual stars. And then we have just some contour plots of the density. And you can see there is a clear bimodality in the right ascension. However, there are little tricks that you can do to get rid of the projection effects from 3D space onto the 2D celestial sphere. These are what we call the proper motion offsets. And what they are is you take the proper motion and you subtract off the expected proper motion at that position on the sky with a known parallax if it was moving with the same space velocity. So you adopt the same space velocities for everything, calculate what you expect the proper motion to be for the position of the star, and then you subtract that off the proper motion. And so you can see here with the contour plots below that what we actually have is just two halves of the same distribution. And that's easily explained when you look on the sky and you see that, hey, right about -16 in galactic latitude, there's a lower density of number of stars. So there's a few stars here, there's a bunch of stars here, and a bunch of stars here. And so this gap basically in stars comes back in the proper motions as this bimodality. So like if stars had an even density all the way across this region, then this bimodality would be gone and you would just see an extended population. I should note that the fact that there is structure here tells us that the stars don't actually have the same space motions, but there's a distribution of space motions. But that's to be expected. And even if you move the space velocities by a couple kilometers per second in different directions, all it will do is just shift the center point of the distribution around, but the shape will stay about the same as long as you're near the correct space velocity. Okay. So the conclusion here is that we do not find them to be separate kinematic populations, but they're actually just the same distribution of stars with just a gap and the celestial sphere throwing a little wrench in the system. And you can we have for a couple of them, there actually is measured radial velocities. And so we can actually calculate the true space velocities. And as you can see in V and U, they are the same distribution. Now in W, you can see that, yeah, okay, there's an offset, right? But they're still the same distribution. They're just the two halves. And that's exactly what we were seeing before in the proper motion, is that there's the two halves just smashed together. And that's what I was saying, that they do actually have different space velocities, but they're related in a distribution. And we'll come back to why there's this offset for the off cloud population. Okay, so we'll start again and we'll do our own study of the region using the Gaia data and see if we can come up with a better population to identify the members of this region. So we're actually going to start off in color space. Here we have a color magnitude diagram from the Gaia. And these are just all the stars within the reasonable area that Gali et al. Identified, and parallaxes, very generous parallaxes within the region. And you can see this, I just love Gaia data for this very thing, is you see this beautiful single star sequence just pops right out. And then you have the main sequence below it. And so this is the sign that these are the young stars. And then here's the main sequence. This red line is the single star sequence of the Tor association, which is 45 mega years. And so you can basically approximately anything above that line should be, or I should say the clusters that have their centers above that line are less than 45 mega years. So we took all the stars from about here at this marked at K4 down to M5 and said, okay, well, let's just take all of these stars that are younger and we're going to look at them kinematically. Oh, sorry, this is me pointing out the problem with age estimates. Like a lot of papers, they sit there and say, well, some of the members are like even older than 10 mega years and some of them are younger. But I mean, you took this data, which had this nice, beautiful sequence, and then you ballooned it out because of all the errors from your SED fitting in your theoretical spectra. And so you really should not believe these error bars right here on this star, saying that this star is going to be less than, or is older than 10 mega years. Yes?
I have a question about that. Yeah, so the comment is that there are some subluminous stars that's because of sometimes extinction disorientation. They do appear very faint.
Yes.
So there could be also luminosity spread due to that.
Yes, exactly. And that's another thing, right? Is you have, sometimes you have disks that are edge-on disks, and those are going to drop the luminosity. And so the star is going to look like it's older, but it's not really older. It just has a disk in the way. Or in some of the stars that are scattered up, those could be just unresolved binaries. Even in the Gaia data, that does happen. They are there, and those will appear over luminous. So the age estimates of a star, of an ensemble like this, you should just not believe wholeheartedly, but what you should do is take the estimate for the whole group and say, okay, well, what does this whole group say? And that's why I was pointing out that it's a little weird that you come up with 5 and 6 because of like this group of stars over here, but over here, these are clearly slightly older. Anyway, back to the kinematics. So these are those stars identified above here, all the stars here, if they have those proper motion offsets within these range and parallaxes, they appear. We threw that Gaussian mixture model at it as well. Why not? And indeed, we do get 2 populations coming out, but this time, while those 2 populations are statistically preferred, they come out and there's not this distinct spatial difference. And really, you look over here and you say, well, actually, that's just because the distribution is non-Gaussian. So of course, it needs more than 1 Gaussian to fit. So this isn't evidence that there's 2 kinematic populations. It just means you can't describe the population with a Gaussian. So those are its kinematics, and now we're going to move on to like a survey to actually find and confirm those new members spectroscopically, because that was actually the original goal of this survey, was to find and construct the most complete census of the region possible with the available data. So we're going to start with the Gaia data again. And so with your eyes, just draw a box around those two ovals and then say, hey, if the star's error, 1 sigma error is within that box, that's going to be identified as a candidate member. So if you recall, these stars were chosen specifically by having their colors correct, but now we're going to ignore the color information and any limits on the magnitude and just say for any star in Gaia, does it have kinematics that are consistent with this distribution? And if so, then we identify it as a candidate. And we come out with about 350 candidates. We also had, and this was the actual beginning, had deep near-R and IRAC imaging. So IRAC on the Spitzer Space Telescope imaged the region at multiple epochs. And then I also got deep 4-star imaging, which is an instrument on the Magellan telescope. And that was available at, I should have put a date there, in 2018, actually. So you see we have quite a bit of time spread from the original IRAC images to the 4-star images. And I measured the astrometry in those images in an extremely complicated way. And you can look up my original paper on that if you're interested. But we measured the proper motions, and the black points are ones that were previously known to be in the Cornet cluster. So I just to remind you, this is the Cornet cluster. So we're not actually doing any of that, a lot of that distribution of younger stars above the Cornet. It's really focused here down just on the Cornet. And there is some overlap with Gaia, but this is specifically looking for stars that are too faint for Gaia. So those are the brown dwarfs, the low mass brown dwarfs, or the planetary mass sized brown dwarfs, or a higher mass brown dwarf or low mass star that's just deeply embedded in the cluster. You're not going to be able to see it with Gaia. And so this complements the Gaia data in that way. We then refine those candidates using color magnitude diagrams, use our extinction corrected diagrams, just a sample of some of them that I used, just constructed from 2-mass data and the wide field infrared survey explorer, yes, WISE. And basically what you do is you put them on here and you draw a line where the known members are. And then if there's any of the candidates that are down below, then you say, well, those are likely not members. And so you throw them away and you refine your candidate sample that way. And then starting in 2017, I have been taking spectra of everything in this region. So for 365 independent objects, and including 42 of the previously known members that had previous spectral classifications. I had infrared and optical data, both for a few stars, but majority just in one or the other. Then you measure their spectral types, you measure their lithium, you compare them to young standards, compare them to old standards, and if they show youth in their spectra, just for those of you that may not know, the infrared is nice. When you see a nice triangle here in the H band, that means it's young, because this is water or steam absorption in the M's. And then, of course, in the optical data, you can look at the lithium lines and the sodium lines over here. And then sometimes when you get things like this that have emission, then that's definitely a young star from like their disk. And so you can tell spectroscopically confirm them that they are a young and and a likely member of the region. So of course, yes, the majority or 95% of the stars identified with Gaia are young. So the Gaia sample is really good, but what it doesn't, it does have some contamination and it doesn't give you spectral types. So that's the advantage over just taking your Gaia sample. And then here's the results. We got 293 new members of independent spectra that say, yes, this is a young star. This is their distribution. The few black points that are here above are just because they're like F and G stars. And so their spectral types are already out there. And so I didn't have to measure them, but they weren't previously identified with the region, except that's not completely true. There was some identified with the region, and we'll get to that in a little bit. Okay, so we have a census of the region. We have spectral types. We have their kinematics. We have their photometry. And so now let's start talking about the properties of this region and of those two populations as we, let's try to disentangle some of the results. For those who don't know, or for a reminder for those that haven't seen this for a while, this is just some models of showing how stars evolve. So specifically, we're talking solar mass and less stars. They actually evolve mostly in luminosity and not in color in the first 20 mega years. So you can see what they're doing. They're dropping to the zero age main sequence down there. And yes, I know I did not satisfy everybody by stopping it before they actually get there, but the point is especially here at like the 0.2 solar mass stars, they're like dropping straight vertically down. And these are the predictions from the models. I should also point out that the majority of the stars in a region are right here, because that's approximately an M5, and that's where most young stars in the star forming region are. And so, here at 15 and 20, you see the solar mass stars start shooting off to go find the G stars when they started out as a K, but there's so few in that sample that you can, just ignore those, and then the rest of them are traveling mostly vertical. So you can leverage that prediction and measure approximately their luminosity. So what we have here is the members of the Upper SCO Stellar Association, which is at a 10 mega year age. And you measure their absolute K, de-reddened, of course, to try to minimize the effects from extinction. They're the gray points. And then this black line here is just the median of that distribution. So you can think of this as this is an empirical model of what the luminosity is as a function of spectral type for a 10 mega year association. And so, yes, there's a lot of scatter, but we're going to talk about medians. And then over top with the red circles, I plot the Ophiuchus star forming region, which is 1 to 2 mega years. And you can see, yes, on average, they are above the black line. So they have and that's a sign of their younger age compared to upper scope. So you can take each star here and measure its distance to this black line, and you can use that as a proxy for age. And once again, I stress, don't believe the individual age of an individual star, but as a group, you see the overall group is shifted higher than upper scope. So you can take it, this is actually from a paper from last year where I did a big study on the Ophiuchus star forming region and some of the potential and proposed populations within that region, and looking at their age to see if there was an age difference. So these are box and whisker plots, except I didn't include the whiskers because there's a lot of outliers and they don't tell you anything. So basically this is the inner quartile range, right? So this is the inner quartile range, and then the middle line is the median. And the advantage of doing this as opposed to just plotting them on an HR diagram and eyeballing it is here you can do things like bootstrapping to say, okay, so how much confidence do I have in the actual median of this distribution? And so you have it here with that delta MK, which is just the distance between this black line and the star for a population, for these different populations. We don't have to go over those. But you then take, to get an age, you take upper SCO from other studies that say upper SCO is 10. So we tie this at 10 and then use the predictions in the different evolutionary models that say, okay, well, how much is this luminosity or the K magnitude going to change with age? To go back, you'll notice that not only are they going vertically, they're all going about the same distance as you move on these different time steps. And it turns out that movement is approximately logarithmic. So this is a logarithmic scale. This is, once again, just hey, everybody likes to have an age in mega years. So this is the age in mega years, but should be used as a relative number, right? So these populations, I am confident that this group of stars is younger than upper SCO. And I would say, if I had to put an age, I'd say it's about 6 mega years or so. So with all those caveats, let's look at the distribution of stars in Corona Australis using that method. So here we have galactic latitude here going along this. On the x-axis and the y-axis here is that delta MK statistic that I measured. And here's their distributions on the celestial sphere, with B going this way again, so you can see. And we'll talk about those red stars in just a second, but you can see that's how they line up here. So you can see where you're going here. This line through the center is approximately the median in the value through this region, and then kind of blue lines above and below with the same distance to just kind of guide your eye. So we see that here in the Cornet Cluster, there's some crazy action going on here, and then out in this region above, there is, in general, just a flat distribution. Now, if you try to measure, well, what's the slope on this? Like these stars over here and these stars over here say that there is a non-trivial slope across this distribution. Oops. But it's hard to believe that in its entirety. So what we may be measuring here is there may be an age spread as getting, so positive means you're getting older here, and negative is younger. And so there may be a general trend of you get older as you move closer to the galactic plane. Meanwhile, here in the Cornet Cluster, these red stars are objects that have high extinction. And in general, the high extinction stars have younger overall ages. And so that you translate it into your head as those are the embedded stars in the actual dark cloud. So the stars that are in the dark cloud with dust and gas around them appear to be on average younger. and this is actually quite a bit younger. Now, of course, you can't cut those. It's not a perfect cut, but it at least provides some guidance. So here we're just going to zoom in a little bit. And so here's those red stars again. These are the embedded stars in the cloud. And then there's these, the black stars have low extinction, and they are literally in the same place as the Cornet cluster, and just a little spread further out. And then here, if we put a line here and say, okay, well, these are the stars that are definitely not on the cloud, and that extends further up for the full distribution. And you say, all right, well, let's calculate the age and say what our medians are. And so those embedded stars get an age that's 1 to 2 megayears. And this is great because that's what previous studies said the Cornet cluster's age was, is that it had 1 to 2 megayears. The problem is these black stars, which are right here in the same area, have a significantly older average age, down at 10 megayears. And then the ones that are further away, this is that possible trend, are even older than 10 megayears, so probably 12, 15 megayears old. Now, the question is, of course, is how much contamination in those different populations are these just young stars from the Coronet that have low extinction that just happen to be on the surface that are pulling this median this way, or is there truly an age spread? And that's something that I cannot tell you with any sort of confidence. But what I can say is the embedded stars or the Cornet cluster is a lot younger than the majority of the stars in the region. So now we'll move on to the kinematics. So here's those, the stars for the full region. From now on, we're gonna see those that have high extinction are gonna be in color, and those without extinction are in the grays and the blacks. So this is the Cornet cluster here. So this is the spatial distribution in 3D space. This is actually approximately what we see on the sky in Y and Z, which makes X the actual distance from us. So how puffy this region actually is. First off, notice that these characteristic error bars, right? This is something else that happens a lot in papers that I read that I get angry about, is people look and say, oh my goodness, look at the spread in the distance of this region, right? So here it's really tight in one direction, but we measure that there's this great big spread actually in distance. Well, that's really just the fact that your parallaxes aren't measured as nearly as well as your on sky astrometry. So that's the purpose of these. So you can use these typical error bars to give you an idea. Interesting to note is that these, so this is basically galactic latitude, and then here X is distance. And you can see that, so here's the Cornet cluster, and then they kind of spread out into that, the young stars above, but there's like this group of stars that's closer. Those actually appeared back in the proper motion. I'll skip ahead. Those are these stars right here. Very interesting. Not sure what's going on there. But here we can have the full 60 motions. And so here I'm plotting like the spatial coordinate versus the corresponding velocity coordinate. And this is that going back to what was causing that proper motion spread that Gaia et al. Found. So here's Z, which is galactic latitude approximately, and here's the velocities along that direction. And you see that there's this trend here for the stars that are further away, or I should say the further away you get from the Cornet, the W measurement decreases. So this is a sign that there's actually expansion in that direction. So you can So the coronet is moving away from those, but once again, in a nice, smooth sort of distribution. So they're not independent, but they're just spreading out with age. And then, yeah, looking at the proper motion offsets, because we don't have RVs for the majority of the stars. And you can see, yes, those high extinction Coronet Cluster members just fit nicely within the distribution. And there's no obvious way to cut these into different kinematic populations. One of the original things, we wanted to look at the initial mass function. This was actually the intention of the original reason of why we started this study to begin with, but here we are, relegated to just a couple of slides. Here, these are color magnitude diagrams of the IRAC field and the 4-star field. So this 4-star field is this little box here, and the IRAC field is where there is multiple epochs of IRAC motions. And then here, this is non-extinction corrected, just near infrared color magnitude diagrams. And if a star failed our criteria for a candidate, or we have a proper motion that says it's likely not a member, we removed it from the plot, and everything else besides known members is a gray points. And so you see there's this beautiful clear, all this space. So this is saying that we're complete down to about here in our survey. And so we're fairly confident that there are no more members with this magnitude range. And then that gives us the idea of how complete our survey was. And here are those distribution of spectral types from our full census. For those different fields, these are the low extinctions in the IRAC field, which is mostly sampling that older population. Here is low extinction for the full survey field. I should say these dotted lines are showing our completeness limit in spectral type, keeping in mind that M5 is about 0.2 solar mass. Then over here, we have the 4-star field, which is mostly sampling the coronet, but if we're doing just the low extinction, then it gets a little messy. Not sure what to say about that. But then here for sample of stars with high extinction, this appears to be mostly the Cornet Cluster, so that gives you the distribution. And lo and behold, hey, guess what? The initial mass function in Corona Australis is the same as everybody else in the region, which is good. Other things we did for the circumstellar disks. This is a procedure that I had established quite a number of years ago for how to study and classify the circumstellar disks using just the infrared photometry from WISE and Spitzer. Basically, what you have is you have the spectral types along the bottom, and then this is K minus those IRAC and WISE colors. So a color relative to that. And so you see here, there's this nice little cluster of stars. Those are the photospheres of stars without disks. And then if they are kicked up here, that means there's excess emission, and that means those are the emission from the circumstellar disk. So you have a line that goes here, and you measure what's the distance between that star and the line for the fit of where the cluster is. Obviously, that line is measured not for Corona Australis, but for more rich populations to give you what we would expect those lines to be, and you plot those in a color excess diagram. So this is how much, this is the measurement of, from here down to where the line should be in the 24 micron, 22 micron range. And then here, this is 12 microns. And you can see that there's actually structure for the types of disks. So these black points are stars that have like a full disk without any major gaps. Now, obviously, ALMA has shown us that there's actually quite a bit of structure and it's not just a smooth thing, but if they're in even sometimes gaps and rings, but if those gaps and rings are not big enough to put a mark in the photometry, you're not going to see it. And so they all get classified as full disks. Well, big, huge open holes or gap are the transitional disks. And then disks over here are stars, are disks that have started to dump all of their dust away and they're just shining less. So we call those evolved disks. And then down here with the green are like second generational debris disks, or they're just the transition from this going down to here, because when you hit 0, that means there is no measurable disk in the infrared. So this is how we classified all the disks in that region. Might as well measure those disk fractions while we're at it to get another handle on the age. So these are the same populations. So this is the high extinction Coronet Cluster here in red. The blue is the stars around the Coronet Cluster but have low extinction, and then the black is for all the other stars above. So this is the answer to all of those problems before, right? The Coronet Cluster is young. It has a high disk fraction. The stars that are above are old. They have a low disk fraction. But if you sample, like that ALMA paper that we showed at the beginning, just any young star in this region, you're going to get a mix. And so therefore, you get inconsistent ages with your disks compared to the stars if you just take those ages that have been measured from the Coronet Cluster. Is so delightful, but this disk fraction for this older population and above fits so nicely in other measurements for regions. So here's upper SCO. Its disk fraction for basically these two bins right here is 0.21. For upper Centaurus lupus, which is part of the SCO-CEN complex, which upper SCO is actually a part of, it's 20 megayears and has a much lower, and it's just so beautiful when it falls right there. It's a tribute to following the same procedure on every region that you measure it for. And that gets rid of all of that scatter from methodology. So this is taken as corroborating evidence that there is that upper Corona Australis. I didn't even introduce the names yet. That the older population here at about 15 megayears is indeed older than upper SCO, like we measured with just the stellar properties. So we get disks and stars giving us the same age. So the practical conclusions. So this is where we say, well, what are we going to call these things? So the Cornet Cluster already has a name. We just say, let's call it the Cornet Cluster. Now, Gaia et al. And myself were beaten anyway, because Gagne in his great work that used a Bayesian model for nearby star forming regions, found actually in the Gaia DR1 that there was a cluster of stars that was near Corona Australis, that was up here, that had motions that were similar, but they said different to Corona Australis. Well, because they were defining it by spatial, right? And so they had, and the first data release only had like the very bright stars. So there's only very few, but they saw it, felt that it was significant, and christened it Upper Corona Australis. So we actually have a name, and I don't have to come up with a new name for the region. So we propose to call all the old stars Upper Corona Australis and the young stars just the Coronet Cluster, and the full region, the Corona Australis complex. The problem, of course, is that Upper Corona Australis extends all the way down and surrounds the Coronet Cluster. But I hope that you are convinced that that is real, that the ages, there's just literally no way I can slice this to make the ages come out right, or consistent, I should say, to not have this overdensity of older stars down here. So there's definitely an overdensity of older stars that is approximately in the same area as the Cornet Cluster. So that's the attributes. So going through these point by point. So we have one population that's a few megayears, the other's about 15. The younger population is located on and in the cloud. The older population surrounds and extends beyond it. The older population has a larger kinematic footprint in kinematic space. The older population is richer by an order of magnitude than the younger. You can approximate with an extinction cut. And so that's what we are doing with the age. And keep it in mind, that's not perfect. But if you want to get a sample that doesn't require you to have an age estimate, then that's what you should go with, is with an extinction cut, to just get with the embedded stars versus the non-embedded stars. And then finally, the disk fractions are consistent with the estimated ages from the stars and evolutionary models. So this proposal solves all the previous age discrepancies of the region, which is what, of course, I am most proud about for this study. In addition, besides those results, we now have a comprehensive census of the spectroscopically confirmed members of the region. This will be part of the paper. It will be available, and it adds another addition of things that one of the things that I've done a lot with my research is construct these censuses. And of course, this was done in conjunction with Kevin Lumen. And so there's some papers where I'm first author, some papers where he's first author, some papers where I'm not on them at all. But you get the ideas. They're just this just beautiful set of all the census of known members, the spectral types, the kinematics, the photometry, the disk classifications, and they will be there and ready to use for any of your comparative study needs. And then an astonishing coincidence that I just wanted to mention because it's too good not to pass off, and then we'll be done. This is going back to my 2020 paper on Ophiuchus. You'll notice that the attributes of Ophiuchus versus Upper SCO are extremely similar to the Cornet Cluster versus Upper Corona Australis. We have a young population with an old population. We have that young population on the cloud, that older population. So these black points are the Upper SCO. And you can see it just comes up and smashes right over and covers Ophiuchus. And so you have stars that are Upper SCO just projected onto Ophiuchus. Interesting. So these, the practical conclusion, of course, is that when you do any studies of Ophiuchus or say the Cornet Cluster, you need to keep in mind that there's likely contamination of an older population. As it turns out, star-forming regions and stellar associations are complicated. So this is actually from Kevin's recent paper that he submitted, where he did a Gaia study of the whole SCO-CEN complex, which is Upper SCO and then these two other Lower Centaurus crux, yes, and then Upper Centaurus lupus. Yes. And you can see that it's actually just one giant related region, right? So these are the these are the candidates identified through the proper motion offsets. You know, you have upper SCO, you have a fucus literally buried right in there. You have those lupus things that the lupus stars that are actually just sitting here projected right on upper Centaurus lupus. There's actually, this is something that somebody else found, spacing their name, but they noticed that there's this huge cluster right here of V1062 SCO of these other, and they all have different ages and they're just spread all over. And so you can see like we're crossing a lot of galactic longitude and latitude here. But here's that coincidence. So these candidates right here that got identified as upper SCO candidates, that's actually Corona Australis. So here it is approximately, as in by eye, I shrunk the image and stuck it on here at about the right scale. So here's the galactic plane, here's upper SCO, and then here's Corona Australis. It turns out Corona Australis's space motions are extremely similar to upper SCO. And that's what this is telling, because these were identified by those proper motion offsets. Are they related to the complex? I don't know, but they're suspiciously similar median space velocities as the rest of the SCO-SEN complex. And at least it's semi nearby. I'll leave that to ponder, and that is it. Any questions?
Okay, yes, thank Taran. Is there any question? Okay. If you have a question, please raise your hand, then we can see your hand, I think. Okay, so Andrew first and then Caitlin.
Yeah, hi. Sorry if this is a bit of an extension, hopefully not actually off topic, but so I noticed you were finding in the older sample a obviously smaller but non-negligible disk fraction. I guess this is sort of interesting because it's sort of in the, getting in the overlap region of where one might consider things primordial versus debris disks. And I guess in particular, there's a Nature paper last week, claiming evidence for a recent collision in disk around, I think it was an A star, 1.7 solar masses, estimated age around 23 million years, so not that far off from what you're talking about. And I guess the claim there was that, and it's partly because it was a more massive star, was that there should be no CO in these disks without a recent collision because of CO depletion timescales. So I guess I'm curious, maybe because of the different masses or ages, would CO be expected in these disks, depending on whether they're primordial versus having ongoing collisions?
So first off, if looking at this diagram here showing the different classifications, right? The stars of the older population tend to be in these more evolved classes. So they're not here with excesses, but they're here and here. So these green ones are those second generational debris disks or just the final late stages of the primordial. So there is still some of that primordial disk in this population because that's what these, or at least they're indistinguishable from the primordial disks. So there's plenty of these evolved disks in that region. To address the second question about whether there's CO, I've written several proposals to try to get Almatyne talking about that very question of, can we detect the CO in these either very late stage primordial disks versus debris disks. And it's hard to know. The naive approach I took back in the day was I would expect there not to be CO in just the second generational debris collisions. But as you just said, those studies are finding that, well, actually, we predict that there should be CO in these debris disks. So I would hazard my current belief is that if you don't find CO, then it's definitely not primordial. And that's about all I can say about that one.
Okay, Caitlin.
Hey, no, mine was really just a comment that I just wanted to say it was a really nice and clear presentation showing sort of the methodology to get to in many ways, not super surprising answer, but very clearly illustrating what we should keep an eye out for when we're reading other people's papers. So thanks.
Yes, thank you, Caitlin. I'm sure you get angry as much as I do when you read those other papers.
I don't know why you would say that.
So to add the comment, whenever Minfang and I have been working on Orion, we were using the same method to basically to derive the age and everything from our spectroscopy, exactly same way of do systematically, same way of dealing with photometry and everything. Otherwise, comparison and comparing the differences of age is very difficult to make if they're done slightly differently. So I hope as a community, we can come up with an idea to actually have some kind of metric to compare those. It's only like, otherwise you have to do all the work again. That's really difficult.
Yeah.
All right, is there any other question? Otherwise, well, let's thank Taran again, and then I will see you next week.